Hello, my name is Naeimeh Vali. I'm a PhD student in Swedish Center for Resource Recovery in University of Borås. And today I will present some of my results during my PhD study on pyrolysis of municipal sewage sludge to investigate char and phosphorus yield together with heavy metal removal that has been done with the experiment and thermodynamic equilibrium calculation. And I'm so happy that I'm participating in the GTT users meeting 2023. The contents today is problem description, methods and material, and the results. The background is related to the phosphorus is a crucial element for all existing organisms and perform a vital function for nourishment, growth, and plant development. It is one of the fundamental parts of fertilizer and has essential elements actually in our organic life. But the problem is the limitation of phosphorus resources and is that phosphorus is a non-renewable element. Yes, we have certain amount of phosphorus in the world, but it is getting more and more polluted with heavy metals. And also, when it's diluted in the water and everywhere, it is so hard to turn it back. And also, it causes acidification and other problems for water. So, phosphorus from secondary sources can be one of the solutions. The world's food production depends directly on phosphorus. The phosphorus that we use today comes from mine and comes to the fertilizer industry and then comes to our food and turns back on toilets and ends up in wastewater treatment plants. Our goal is to close this loop to have a phosphorus recycling. And why municipal sewage sludge? As can be seen in this table, a municipal sewage sludge has the highest level of phosphorus among other waste. And what is municipal sewage sludge? Is the main byproduct of wastewater treatment plant that has been generated in large quantities over the past few decades. And it is highly contaminated with heavy metals, organic pollutants such as pathogens, dioxins, microplastics, and antibiotics. And according to EU legislation directive, municipal sewage sludge should not be directly applied in a farmland application. So the pyrolysis can be one of the treatments for municipal sewage sludge. It is a thermal treatment at temperature between 300 and 1000 degrees in absence of oxygen. The products are gases, biochar, and bio-oil. Biochar is a carbon-rich product with different applications, mainly as a soil improver or a fertilizer. And pyrolysis also cracks organic pollutants and immobilize heavy metals and recover remaining nutrients in the biochar. There are many potential applications across various fields, including agriculture, horticulture, energy, environmental remediation, livestock feed, water filtration, and aquaculture, and waste management for biochar today. However, there are some challenges also for using a sewage sludge biochar. As you can see here, there are some legislative barriers, organic contaminants, challenges regarding inorganic contaminants, phosphorus recovery, and market challenges. What I study is on inorganic contaminants and phosphorus recovery. And inorganic contaminants consist of heavy metals, which is can be found highly in sewage sludge, and it is varies between different wastewater treatment plants as a result of different treatment and also based on the location. Some heavy metal will be concentrated in a biochar, and some biochar or batches cannot be used in agricultural application. But there are some alternative uses, such as construction material for these biochar. And also, the phosphorus recovery with sewage sludge is another challenge that we have. The phosphorus availability for the soil is important. And also, there are some regulation that might be changed, will be changed in the EU in the future, that phosphorus recovery would be mandatory. As we can see in sewage sludge, we have phosphorus in form of organic phosphorus and a pyrophosphate and orthophosphate. And then after pyrolysis, we could have it in form of orthophosphate. In this study, there are different steps. As you can see here, the first step was the collection of the municipal sewage sludge from 3 different wastewater treatment plants in Sweden, Mora and Borås and Lidköping. And the next step was the drying of the municipal sewage sludge in the lab, and also performing chemical analysis of those sewage sludge. And the next step was the pyrolysis of the municipal sewage sludge and preparation of the biochars. Also, we have done chemical fractionation together with the thermodynamic equilibrium calculation modeling, and also doing the chemical characterization of the biochar. And today I will show you some of the results with the modeling. As I said, we used sewage for the thermodynamic equilibrium calculation, and as a sewage user, I know that you are familiar with the sewage, and it is included oxide and metallic solid phases and different solution and different type of liquid and gaseous phases. Here is the schematic of our rotary pyrolyzer in our lab. And the pyrolysis actually has been done at different temperature, 500, 700, and 900 dC. For it is a kind of continuous feed, and for every batch we had 500 to 800 grams. Different sections for this pyrolysis unit can be seen here. It is equipped with thermocouples to be sure that the temperature is even during the pyrolysis. As I said, the modeling strategy was the combination of chemical fractionation and thermodynamic equilibrium calculation. So after chemical fractionation analysis, the less reactive ash-forming elements that remained in the solid residue, as you see in the picture, were used as an input data for our calculation. The calculation was performed under a nitrogen atmosphere, and the pressure was 1 atmosphere, and the temperature was between 500 and 1000 according to our experiment. And the char and gas actually were our focus. And then for the experiments, we also characterize the biochar, the resulted biochar after pyrolysis at different temperature using microwave plasma atomic emission. That before that, it has been the biochar has been digested by acid cocktail in a microwave oven, and then it was analyzed by MP for interesting elements. Some of the results, here you can see the characteristics of the municipal sewage sludge. The lead shopping sewage sludge, actually the phosphorus removal method in wastewater treatment plant was by chemical phosphorus removal, and it was undigested. And for borose sewage sludge, it was anaerobic digestion and biological phosphorus removal had been done on the sewage sludge in the wastewater treatment plant. As you see, the ash content in the borose sewage sludge was higher than lead shopping, and it was as a result of losing some of carbon during anaerobic digestion in a wastewater treatment plant, and some of carbon released into the gas. The result from chemical fractionation, as you see here, the concentration of each element for different color here shows the concentration of each element. And for example, in water and ammonium acetate and solid waste, and also in the sludge. And as I said, the less reactive ash-forming elements, the proportion of the less reactive ash-forming element in the red color were used to do the modeling as an input data. So, the elements which has been contributed to the calculation were hydrogen, carbon, nitrogen, oxygen, sodium, magnesium, aluminum, silicate, phosphorus, potassium, calcium, iron, zinc, and sulfur. And all calculations were performed with the software FACSA 7.3, which is based on minimization of Gibbs free energy. The databases that we used, it was GTOX and SGPS. For the GTOX, the solution model and a slag, which was liquid phase containing oxide, metal, sulfide, sulfate, and then different solution phases, as you see in the table. For the gases, carbon dioxide, water, and hydrogen selected from GTOX, and also stoichiometric solid compounds. And data and SGPS, for the SGPS, we selected gas compounds and stoichiometric solid compounds from SGPS. Here in this picture, you can see from the results from thermodynamic equilibrium calculation modeling, showing the biochar yield at different temperature. As you can see here, at a temperature between 550 and 600, the char yield showed a decrease. So by increasing the temperature up to 750, the rate of mass loss declined constantly. So there was an almost constant yield, as you see, between 750 and 850. And the most sudden mass loss occurred around 850 and 900 degrees C. The total, so from 500 to 1000, the total char yield decreased by 30% based on thermodynamic equilibrium calculation. That was in a good agreement with the experiments. Here is the results from thermodynamic equilibrium calculation, showing the recovery percentage of various nutrients such as carbon, phosphorus, magnesium, potassium at biochar pyrolyzed in different temperatures from 500 to 1000. As you can see, the amount of carbon decreases by increasing temperature. Magnesium and potassium are almost constant. Phosphorus is still 100% recovered and remained in the char until 850, and then it starts to release slightly. And as you see, the carbon, as you see in here in this picture, in this graph, you can see the gaseous carbon, hydrocarbon that has been produced during pyrolysis at different temperature, and showing that carbon goes to the gases even before 500 in form of carbon dioxide and carbon monoxide. But regarding phosphorus, as you see, and it has been shown by thermodynamic equilibrium calculation with this graph, that from 850 it starts to release slightly into the gases in form of CHP and P2. And the results here for the calculated equilibrium composition of slag compounds, liquid species during pyrolysis, sewage sludge at different temperature using thermodynamic equilibrium calculation shows that the phosphorus slag compounds start to form at 650 and then release into the gas at temperature at 850. So this is the different, shows that the phosphorus slag actually start to form at 650. And in the last slide, we saw that phosphorus from thermodynamic equilibrium calculation, but with our modeling, they start to form a phosphorus and CHP gas species at temperature of 850. And other form of compounds that phosphorus can be found together with potassium, zinc, aluminum, and instead potassium then goes to together with potassium, it starts to form K4P2O7, as you see here. The calculated equilibrium composition of solid phosphorus compounds can be seen here. They are the solid solid phosphorus contain compound, and as you see here, the potassium, these compounds, potassium, phosphorus, magnesium oxide, this is the most stable stoichiometric solids from 500 to 1000, we have it. And then the highest mass fraction of phosphorus can be found in the aluminum phosphate compound, and it was expected due to the phosphorus precipitation process in the wastewater treatment plant that they have used aluminum-based chemical. So this one, this aluminum phosphorus compound that has been simulated in the chart. Here is the results for the solid and slag in organic matter in the lead shopping sewage sludge and also borough sewage sludge. Again, we have the potassium, phosphorus, magnesium oxide, which is the most stable from thermodynamic point of view. And we have other combination of phosphorus with magnesium, calcium, and potassium that we are interested to have it in the biochar for the agricultural usage. The results of my study, these studies has been published in these two publications, and I'm working on the next calculation, which is modeling of the heavy metals. I would like to have an acknowledgement toward my supervisor, Anita Peterson, and also Rainer Packman and Sedi Bigdeli, who was actually who was always supportive and make it possible for me. And here is my contact details. and thank you for your attention.